And Cynthia, is it okay if we record your talk
Sure.
and actually make it available on our YouTube channel later?
Yeah, that's fine. I'll try not to say anything too stupid.
Sure. Or we'll let you override later.
Okay. So just to remind me on the timing, so I'm going to talk for probably about 45 minutes, I think.
Sure. I mean, so the whole event is scheduled for an hour. So
okay, great. Good.
45, 50 minutes, and then having some questions after that will be fine. Yeah.
Okay, great. If I have a little extra time at the end, I have a demo that I can show. Yeah, if I have time for it, I'll do it. We'll see how we're doing on the timing.
Sure.
Okay.
I mean, we are okay to go a few minutes over time. I mean, it's up to you.
Okay. So when I get there, we'll see how we're doing.
Yes.
Okay.
Is it okay to get started?
Yeah, go for it.
Okay. So good evening, everyone, and welcome to RBCDSAI. This is the fifth RBCDSAI LatentView Colloquium series. And so we have been having a lot of wonderful speakers so far in the Colloquium series, and it really gives us great pleasure to host Professor Cynthia Rudin. So Professor Rudin's work on interpretable AI, right? So, I mean, she has been one of the pioneers in this space, right? I mean, she was doing interpretable AI before it became hot. So we have been following, I mean, at least in my group, right? So we have been pretty inspired by her work. So Professor Rudin is a professor of computer science, electrical and computer engineering, statistical science, and biostatistics and bioinformatics at Duke University. And she directs the Interpretable Machine Learning Lab there. And previously, Professor Rudin had held positions at MIT, Columbia, and NYU. And she's a 3-time winner of the Inform's Innovative Applications and Analytics Award. And she's also been very active in the Informs and AI and the data mining communities. And she served on multiple committees, as well as given keynote invited talks at various conferences. I've had the pleasure of listening to her at least a couple of times. And very recently, she is the recipient of the 2022 AAAI Squirrel AI Award for pioneering socially responsible AI. I read that in one of her interviews, she said that she was very surprised to receive the award. And I think you were probably the only one who was surprised, I mean, not for a lot of us. So, so that is an interesting connection between the Squirrel AI Award and IIT Madras, because before Professor Regina Barcelay got the Squirrel AI Award, we had hosted her here for a talk. And we did invite you before the award was announced. So inviting people over here to give talks seems to be like a harbinger of the award later. And I'm really happy that you agreed to do the event with us. So over to you, Professor Rudin.
Thank you. Let me just share my screen really quick.
Sure.
There we go. Okay, cool. Okay, so bad stuff is happening now. There are bad bail and parole decisions being made because people typed the wrong number into a black box model. It is letting dangerous people go free, and it's keeping people in prison who don't deserve to be there. There are algorithms that are, being used for medical diagnosis and screening. Some of these algorithms are FDA approved, and then they don't work when you launch them in practice. So here's an example where an algorithm is depending on a factor that's not allowed, which is like a word in a medical image rather than the actual medical content of the image. There are bad credit and loan decisions being made based on faulty information. And I claim that explainable machine learning perpetuates this problem. Now, I want to make a distinction between explainable machine learning, like explaining a black box model, and designing an inherently interpretable model. So an interpretable machine learning model obeys a domain-specific set of constraints that makes its computations easier to understand. And so I want to contrast interpretable machine learning, which is when you use a model that is not a black box, with explainable machine learning, which is when you use a black box and then you try to figure out what it's doing afterward. You explain it post hoc. So in explainable machine learning, you might start with some complicated formula that you don't understand, and then you might either create a model that approximates it, compute derivatives of it, visualize what part of the model, but part of the input the model is paying attention to, or just basically, do some other computation that justifies the existence of this black box. Try to understand what computation it's doing. Now, I claim that these are really quite different. In fact, there's a chasm between these things, and most people don't see that. Most people they think, oh, these are almost the same, but they are very, very different. And I claim that that interpretable models are really, like, those are the ones you can use in high stakes decisions. I wouldn't, unless it's a very specific kind of decision where you don't need an explanation, I don't think we should be using black boxes. Okay, so why are these two things so different? Well, first of all, we don't really need black box models in the first place. So I'll talk a lot about the accuracy interpretability trade-off and the fact that there's not really any scientific evidence for it, because we've always been able to create interpretable models of the same level of accuracy as black box models, even for questions like computer vision. And then also, explanation models lend authority to the black box rather than suggest that you replace them with an interpretable model. And the explanation methods tend to be flawed. So I put this slide up very briefly a minute ago, but I want to describe it a little bit more. So in this article, this is a New York Times article that describes the case of Glenn Rodriguez, who was denied parole because of a miscalculated COMPAS score. Now, COMPAS is a proprietary model that's used in the US justice system. So no one knows exactly how it's making its computations except the company that created the model. And, I don't know, the person who's being subjected to it does not know what the computation is. And in this case, he was denied parole because of his criminal history features were typed in wrong to the COMPAS score, and he wasn't able to check that sort of before his parole was denied. So here we have a black box model that's used in the justice system. It's used very widely. How accurate is it? Luckily, there was a very famous data set that came out several years ago from Florida, and that data set will allow us to determine how accurate COMPAS is. So we took the COMPAS data from Florida and compared its accuracy to the latest machine learning model in our lab at the time, which was Corals. So Corals came out in 2017. And so we took the Florida data, which was basic demographic and criminal history information for each individual who had their COMPAS score calculated in Florida within a certain set of years. And Corals produced a model that was so tiny that it could fit on the bottom of a PowerPoint slide. So I'm going to show you this model. So Corals produces optimal one-sided decision lists. So these are if-then rule models. So this is the machine learning model. This is actually a model that came out of an algorithm. It's not just a rule of thumb. It actually came out of an algorithm. And the model says if the person is 19 to 20 years old and male, predict arrest within 2 years of their COMPAS score calculation. Else, if they're 21 to 22 years old and they have 2 to 3 prior offenses, predict arrest within 2 years of their COMPAS score calculation. Also, if they have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this and thought, how could this possibly compete with COMPAS? Is it as accurate? And as it turns out, it was. So I'm showing you tenfold cross-validation results. So these are results on the test set, and each fold that we tested on, so 1/10 of the data is in a different color. So you can see that the different folds here. And as you can see that even across these random splits of data, Corals and COMPAS are about equally accurate. And we thought, okay, fine. Well, let's take this data set and launch the entire machine learning arsenal on it and see if we can get any more accuracy. And as it turns out, we couldn't. So some of these methods produce models that are so complicated that you can't even put them on a PowerPoint slide. So for instance, boosted decision trees with hundreds of trees, that's this one. Support vector machines with radial basis function kernels, random forest. Right? These methods produce big, the calculations are so many that you can't even put them on the slide. And then you compare that to Compass, which is a complete black box, don't know what it's doing, and Corals, whose whole model is right there in the corner of the slide. So now there was a huge debate in the United States about the algorithmic fairness of Compass, but the truth is that we just don't seem to need Compass at all. So, why are we still using it, right? Now, I want to get back to this point I made earlier that the accuracy interpretability trade-off doesn't seem to have any real scientific evidence proving that it exists, right? So I want to put up this slide from the DARPA Explainable AI BAA. And this slide, I just really have problems with this slide. This slide gives me it just makes me cringe whenever I see it. Okay, so what is this slide supposed to represent? It's supposed to represent that there must be a trade-off between learning performance and explanation effectiveness, because you've got the most accurate models, which are over here, having low explanation effectiveness, and the worst learning performance with the best explanation. And I looked at this and I thought, what in the world is going on? First of all, there's no quantification on the axes. So I don't know whether this corresponds to any real data set. I don't think this figure actually represents a real problem. That's one issue with it. Second thing, this figure seems to correspond to working with a fixed data set and a fixed evaluation metric. And that's maybe what you would look at if you were doing Kaggle competitions, or if you were writing a paper with an experimental section where you wanted to prove something. But that is not how we do things in the real world. So in the real world, we work with a data science process. So I've put here the knowledge discovery and databases process, the KDD process from 1996. And even in this process, the final step after you do data mining is interpretation and evaluation. And then once you look at the results, you're supposed to go back and change the way you're processing the data and the way you're doing data mining so that then at the next iteration of this process, you will improve. So the fact is that this whole idea of a static comparison is not the way we would do things in the real world. And in fact, better understanding of what's going on can help us have an overall better performance for the whole system. Okay, so that's another issue I have with this figure. A third issue is that the trade-off doesn't happen like this. So even for, like I said, deep learning and computer vision, we've been able to get models that are just as accurate as the best models out there for computer vision that are actually interpretable. So I think this line is relatively flat in reality. And then also this figure, it's not even clear what they're talking about. Are they talking about explaining black boxes or designing inherently interpretable models? For explaining black boxes, you'd get some approximation error, and so you would maybe find a trade-off. But for inherently interpretable models, there wouldn't be such a trade-off. So it wasn't really clear what they were talking about even in this figure. And I think from DARPA, I think they were talking about explaining black boxes. Okay, so there's not really any scientific evidence for this trade-off here, but there's some subtlety to this argument that I want to provide to you, which is that there's really two types of data that we use in machine learning. There's tabular data and raw data. Tabular data kind of looks like this, where you've got categorical or real valued outputs, and each of the features are interpretable. Whereas raw data are things like images or sound waves or text, where one pixel is not going to tell you anything about the outcome, or about the label, about what's in the image. Now, these two different types of data require different types of explanations, right? Different types of ways of understanding the data, but they also require different techniques. So for raw data, the only technique that's working right now is neural networks. And that doesn't mean we can't make them interpretable, but that's the only technique that's really working right now for that data. Whereas for tabular data, with binary preprocessing, all the methods tend to have similar performance, and that includes very sparse models, including tiny little decision trees like the corals model I just showed you, or scoring systems, which are sparse linear models with integer coefficients. Okay, so the fact that these tabular data problems, for these problems, we can use pretty much any technique we want, gives us really an opportunity to create very simple models. So on the next set of slides, I'm going to show you an example where we created a very tiny little model that is used in a very high stakes decision-making setting. So this problem is to prevent brain damage in critically ill patients. So let's say that you have an aneurysm in your brain that bursts, and so you have like, you know, a hemorrhage, like a blood explosion in your brain over here. And then at that point, you'd go to the hospital, get surgery, you'd be in the intensive care unit. They would put continuous EEG monitors all over your head, and you would be monitored for the possibility of getting a seizure. These are subclinical seizures, so they're just in your brain. It's not like the patients are shaking, right? This is just in their brain. So CEG is the only way to detect seizures and seizure-like activity. Now, the problem with these using EEG for this, right, is that you need to use EEG. You have to use it, but the EEG equipment and people minding that equipment, that resource is limited. And so these monitors tend to stay on patients way too long, and then patients who need them don't get them. So we worked with doctors, neurologists who work in the intensive care units in these hospitals to design a predictive model for seizures. And that model is called the 2 helps 2B score. And we designed 2 helps 2B so that it's small enough to fit on a PowerPoint slide, but it's just as accurate as our best black box machine learning models for the problem. So this is 2 helps 2B. So this is 2HELPS, and then 2 points for the B, so that the neurologist can memorize the model just by knowing its name. Now, 2 helps 2B is, like I said, it's an actual machine learning model. It was not created by doctors. It looks like a rule of thumb, but it's a full-blown machine learning model. This was created by data fed into an optimization problem. It's an actual machine learning model, just as accurate as our best black box model. It's not like a black box in that, like a black box sort of forces you to trust it, whereas here doctors can decide for themselves whether they want to trust it. They can also calibrate the score with information not in the database. So they could say, you know, there's an unusual situation and that might adjust, you know, the point. I might give an extra point for such and such. Okay, so, and the score can be explained to non-physicians so that you can, you know, tell someone why their relative is being taken off EEG monitoring, for instance. So you'll see that there's only like 6 features here, but the database that we built it from was huge. It was over 70 features. And then the algorithm itself that we worked with produced the point scores and figured out which 6 features to use here. Now, the algorithm that we created to design this model produces risk scores. It's actually quite a complicated model. I'm just going to show you just in case you're interested in the math here. So there are sort of 3 goals in this optimization problem. One is try to keep the model accurate, which is this term. This term says, please keep the model small, like choose as few terms as you can while keeping it accurate. And then this set of constraints over here means that all of the coefficients have to be between -10 and 10 integers. And if you are an optimization expert, you'll notice that this is actually a mixed integer nonlinear program. It's actually a really hard math problem. And so we designed a specialized technique to solve this problem. But my point here in showing this slide is that this should be the problem of the computer scientists to solve and not the doctors, right? If we don't solve these problems, then it makes the doctor's lives harder and the patient's lives worse. And so we really don't want to do that. We want to solve these problems so that we can help doctors make decisions that are best for their patients. Okay, so great. So now what happens is that you, with your burst aneurysm and your hemorrhage, you come in, you're being monitored on CEEG. The neurologist looks at you and says, oh, I see this, this, and that. Your 2 helps 2B score is 3, you're high risk. I'm going to place you on continuous EEG monitoring for at least 72 hours and start you on preventative medications for seizures. Now, so far, the 2 helps 2B score has been validated on an independent multi-center cohort. This is not a study I was involved in. The neurologist did this independently. And the method has been implemented at several hospitals. It's available on platforms like Medscape, and it's resulted in a substantial reduction in the duration of EEG monitoring per patient, which really allowed the doctors in their validation study to monitor a lot more patients than they were monitoring before, which according to the doctors helps reduce brain damage and save lives. So it's a rare example of when a machine learning model is used in a very high stakes decision-making setting. All right, so so fine. We understand now that for tabular data, there's a lot of opportunities for building very interpretable models. So what do we do in this case when we have raw data? Like what happens if we're working in computer vision or something? Do we need to explain black box models in these cases, right? Now, let me tell you what the reason why I don't think we should be explaining black box models. I'll give you an example, which is the use of saliency maps. So a lot of people have been trying to explain neural networks, and it doesn't really work very well because neural networks are not designed to be explained, so there's no reason why they naturally should be interpretable. So I'm just going to give you an example of a type of explanation that I think is particularly bad. So this is a computer vision model. It's classified this image as a Siberian Husky, and we ask it why, and it highlights this part of the image and says, this is why. And we say, oh, that looks like a pretty good explanation. It's highlighting the part of the image that we would expect it to highlight for why this image has a Siberian Husky in it. But then we ask the network, okay, what evidence do you have for this image to contain a musical instrument? So we say, what evidence do you have for this being a transverse flute? And it highlights almost exactly the same region. So it's giving you almost the same explanation for a completely different outcome. So it's just not good. And this type of explanation is particularly bad for popular techniques like GradCam, where people have seen that it highlights stuff all over the image when the network is actually using some very specific bit of the image. So the problem also is that there's lots of work in radiology on attention maps right now, and this makes me very nervous because I don't want radiologists to see these explanations and then make an opinion based on them. All right, so how would we design an interpretable deep neural network? We've been proposing at least 2 methods for doing this. I'm going to show you one of them, which uses case-based reasoning and uses, it's kind of like k-nearest neighbors, but it's like k-nearest parts of prototypical cases for that class, okay? So this is our neural network, ProtoPNet, and it's explaining to me why it thinks this bird looks like a clay-colored sparrow. And it's saying that this part of the bird, right, the top part of the bird, here, the top part of the bird, looks like this part of that bird. And this is a prototypical clay-colored sparrow. And it says the belly of the bird looks like this part of that bird, and this is a prototypical clay-colored sparrow. And then this part of the bird, like the edge of the feathers there, looks like this part of that bird, and the feet looks like this part of this bird. So it's saying here that, well, I think this is a clay-colored sparrow because this looks like that, and this looks like that, and this looks like that, and this looks like that. And that's how the network is actually reasoning about the image. This is not a post hoc explanation. The network is actually getting points for each of these comparisons and adding up the points. and that's why it's saying, I think this looks like that, and my total evidence is such that I think this bird is a clay-colored sparrow. So anyway, we decided that since this network was saying this looks like that, and this looks like that, and this looks like that, we would call the paper this looks like that. So what the network does is that it adds a prototype layer to any black box. You can take your favorite black box deep neural network, and it forces the network to do case-based reasoning, and the prototypes are learned during training. So let me just show you kind of the picture of how that actually works. So this is just a diagram of your favorite black box convolutional deep neural network. And let's say it's pretty accurate, okay? So then what we would do is we add another layer we transform it to be interpretable by adding a layer just before the last fully connected layer. And that part of the network, it's forcing the network to do these comparisons between the image that comes in and the prototypes. So it sort of scans the image, looking for parts of it that it thinks looks like the prototypes. And everything is learned here. The prototypes are learned. They don't come from domain experts. They're actually learned by the network during training. So let me show you kind of how this reasoning process works, because I find these diagrams very difficult to understand. So I'll just show you how that reasoning process works, okay? So here the network is explaining why this bird is classified as a red-bellied woodpecker. And it says, well, I think this part of the bird looks like this part of that bird. And it's giving it two numbers for that comparison. One is how close this looks like that. So that's this 6.499. So that's the similarity between this and this. And 6.499 is actually a really high number. So it's seeing this like red thing on these birds' heads and saying, I'm going to give that a high score because that really looks, it's very similar to me. So it gets this score for that comparison of this to that. And then there's another number here, which is the importance of this image to the red-bellied woodpecker class. So this is telling you how important this prototype is. Okay, so we have these pairs of numbers. We have like, okay, the feathers over here, looks like those feathers over here. That number's, the comparison is getting 4.392 points, and then we multiply that by how important this prototype is to that class, which is this number here. Okay, and there's 20 numbers in the sum, and then the total is right here, so it's 32 total points for the red-bellied woodpecker class. And then for the next highest scoring class, which is a red-cockaded woodpecker, it can't quite get as many points because, as you can see, apparently red-cockaded woodpeckers don't seem to have red heads, and so it just can't get the extra points from like the comparison with the head. It gets points for the feathers because apparently the feathers of these birds look similar, but it just can't get as many points because of the lack of the red head. And so that's why it says, all right, that's a red-bellied woodpecker. All right, so then I'm going to show you a case where things don't go so well for the network. So this is a bird. This cute little bird is misclassified. The network thinks it's a prothonotary warbler instead of a Wilson's warbler. So what happened here? So it looks at this bird and it's sort of zooming in just to like the eye and the beak, and it's looking at the kind of the way the eye looks and the placement of the beak, maybe the yellow color, I don't know, maybe something about the wing pattern. It doesn't get that many points. Whereas for the prothonotary warbler class, it's looking at like kind of maybe a little bit more of the head, and yeah, it's looking at kind of the whole head and the yellow kind of, I don't know. So it's getting a little more points for that one. And you think, what's going on here? Why is it not classifying this correctly? Now, as I mentioned, this network, this method works for any black box model, okay? And so what I'm going to do in a second is I'm going to switch that DenseNet 161 out, which is our black box that we started with. I'm going to switch it to a different one, and you'll see something different. But I want to point out that when you look at these figures, like at least when I look at these figures, I actually think this bird looks more like a prothonotary warbler than a Wilson's warbler. But Wilson's warbler is correct. But to me, looking at this, that really looks like a prothonotary warbler. So I can understand why the network got that wrong, you know? But you'll see in the next slide what's going on. So I'm going to swap out this for a VGG 16. And then this time, when we look at the Wilson's warbler class, so it actually gets it right this time. And here it's looking at, like, the placement of the eyes and the beak, but you can see it's avoiding the head. Now you see why it's avoiding the head, because Wilson's warblers, apparently they have a black spot on the top of their head, and this guy doesn't really have that. And I think maybe it's because he might be a baby Wilson's warbler or something. He just doesn't have that black spot on the top of his head, and that makes him look like a prothonotary warbler. Okay, so this data set that I've been showing you is actually a benchmark data set in computer vision. That's where the kind of deepest of the deep neural networks are trained and tested. And on this data set, we're seeing that the original black box accuracies for all different black box models is somewhere between 74.6% and 82.3%. Whereas when we take those models and make them interpretable by adding the proto-PNet layer, we're seeing a very similar set of accuracies. And then if we take several proto-PNets and put them together, like just stack them so that instead of 20 prototypes, you have more than 20 prototypes, it's still interpretable in the sense that it's still using prototypes and doing these comparisons, but it's giving us an accuracy that's better than any of the black boxes. So what I'm saying is that even for computer vision, we can still have an interpretable model of the same accuracy as a black box. So I have yet to find a domain where I actually need a black box. Okay, so after we did this work, we were thinking like, okay, we now have a computer vision algorithm that's interpretable, that's accurate. So as you know, I like to work on applications. And so we were wondering like, okay, what do we do with this? Like, now that we have it, where can we use it to help people, right? So we decided that we would do computer-aided mammography because we were worried that the radiologists keep doing the saliency map stuff. And so we thought, okay, well, let's at least show them what we think an interpretable deep learning model for radiology might look like. And I don't know, what's going to happen with this in the future, but I think it's definitely better than what they're trying to do right now. So as you know, mammography is a leading cause of death, not just in the USA, but everywhere else. It's causing hundreds of thousands of there's hundreds of thousands of cases diagnosed, at least in the US each year, causing tens of thousands of deaths. Mammography is the hardest task in all of radiology. Radiologists miss a fifth of breast cancers. Half of women getting an annual mammogram over 10 years will have a false positive. Up to 3/4 of biopsies come back as benign, in other words, potentially unnecessary surgeries. We also know that healthcare is not distributed evenly across the world. And so that's why we thought this problem would be useful to work on, because maybe we could take the knowledge that we have at Duke and kind of, spread it around the world. All right. So an uninterpretable deep learning approach would take a mammogram and it would say, okay, for this image, the probability that this lesion is malignant is low. Let's predict benign and not give any reason for it. Okay, so that's the black box approach. The saliency approach is not much better. It would say, take this lesion, predict, probability of malignancy being low because blob. And of course, we already knew that there was a lesion there, so that's not really helpful. So we designed a new method. This is called IAIABL. And what this does is it uses the proto-PNet approach, where it takes the image and breaks it down and it forces the network to look at parts of the image and make comparisons to prototypical cases. So here it says, I think this part, this part of the lesion looks like this, prototypical indistinct margin. Indistinct margins are bad. We're going to add a little bit to the malignancy score. Whereas this part of the lesion looks circumscribed. It looks like this circumscribed lesion. And so we're going to subtract something from the malignancy score because circumscribed is good. Okay, so yeah, so that's what we've been kind of working on in the medical sphere lately. And I'm just, we don't have enough data right now on this project to really make this into something that could be launched out into the world, but other people do have that data. And so what I'm hoping is that by just sort of putting this out there, putting this idea out there and showing that you can get accuracy with this, that people who do have data will try to adopt this. And of course, all of our code is public. Okay, so let me kind of ask a question, which is, okay, so if black boxes were going to be more accurate than interpretable models, where would we see that? So the first answer to that question you'd think would be interpretable, neural networks from computer vision. And we already talked about that. And what we found is that interpretable neural network accuracy equals black box accuracy. So let's go with, let's test it another way, right? So if you could see this anywhere, you might see it in really hard benchmark data sets, right? This is where we train and test machine learning algorithms. So, we should be able to see this in benchmark data sets. And so what I'm going to do is I'm going to show you, I'm glad I got to this point in the talk with a little bit of time because I want to show you this benchmark, the results that we have on this benchmark data set. So this is the Explainable Machine Learning Challenge from 2018, where FICO provided a HELOC data set. So this is a loan data set. They gave us, so all the competitors in this challenge, they gave us 10,000 loan applicants, a lot of factors about their credit history. If you take this data set and you run lots of different machine learning experiments on it, you get that the best accuracy is going to be about 73%. And if you're looking at area under the curve, which is another kind of way to measure the quality of your predictions, the best accuracy we got was about 0.8. Okay, so those are the special two numbers. That's black box accuracy. And the question is, can we get that with an interpretable model? Now, the first place in this challenge, they actually provided a tiny little model, but they broke the fundamental rule of interpretable machine learning, which is that they lost performance. So their accuracy went down a little bit, and their AUC went down a lot. Okay, so remember, 0.5 is random guessing, 1 is perfect. So 0.62 is not that good compared to 0.8, which is where it should be. So our technique that we provided won the FICO Recognition Prize, and it achieved an accuracy that was around the same as the black box, and the AUC was just as good as the black box. So we didn't sacrifice any performance to get into. Now, I want to point out that data science competitions are totally different than like working with a domain expert in reality. So we had no idea what these judges were looking for. And we completely misinterpreted kind of what they might have been looking for because we didn't have any interaction with them. So we went to their webpage, we went to like the FICO webpage to try to figure out what they might like, and they had lots of neural networky stuff on their website, and we thought, oh, maybe they would like something that looks like a neural network, but that's actually an interpretable model. So we designed this thing that we thought they might like just based on their website, but it turned out that they didn't actually let people interact they didn't actually let the judges interact with the models during the competition, which was really a shame for us. We were kind of sad about that. But anyway, so I'll just show you a little bit of what our model does. I have like this big screenshot of what the model looks like. But essentially there were 10 subscale scores. We did like 10 little itty bitty logistic regression models. So we had like, this is the delinquency subscale, which involved 4 factors. So we would predict a delinquency of 79.9% just based on like 4 factors. And I'm going to show you what those 4 factors are. They're things like percent of trades never delinquent and months since most recent delinquency. We would give each person points based on their like delinquency information. Points would get added up, and that would get this number, and then we'd add a bias term to it. So add these 2 numbers together, send that through a logistic function to get the risk score, which was 79.8%, which is that number there. And so actually, now I have a little bit of time, so I'm going to eat into a little bit of my question time to kind of show you that, because I wanted to show this demo. I haven't done this in a while. So this on the Duke website. So after the talk, you can go to this website right here, and you can click where I'm clicking. So if you go to models, and then this is all the different factors about people's credit history, and you can fiddle around with those yourself. I don't feel like putting in 42 numbers, so I'm just going to grab one of our demo people and like put their numbers in. And then when I run the model, it's going to do a bunch of computations on the Duke server, and it's finished already. And it's coloring these by the risk. Okay, so scale, which has again 4 factors in it out of these like 22 factors. And if I click that, it brings up the different points for this person and shows you this computation that went into that 79.8%, the same one I was showing you earlier. Okay, and then the total score is a linear combination of just the 10 subscale scores. So here's that, this is like a 79% or whatever, and then it has a weight on it, and then these 2 numbers get multiplied together, and gets points, added the points, and that brings this person's total risk to 95.22%. Okay, so yeah, so that's what we gave to the judges. We also had like a bunch of other stuff, like the most important factors, which are all colored here. Like you can just scroll through this and see that delinquency really contributed to this person's bad risk. And then we had like, you know, some rules that said like for all 594 people who had like a bad external risk estimate, and they were only, their average number of months in the file is small, like they're recent, then all of them were predicted to default on their loan. So we did all this kind of cool stuff that we thought the judges would like. So it was really kind of a pity that they weren't able to interact with our thing. But luckily FICO realized the problem, and then they sort of changed their judging criteria. Okay, so anyway, back to where I was. Great, so this is where you'd expect to see black boxes be more accurate than interpretable models. But in both cases, the interpretable model's accuracy was equal to the black box accuracy. So there's really no scientific evidence that there is an accuracy interpretability trade-off at all, right? You don't need to sacrifice predictive performance for interpretability as long as you're good at optimizing, and that you can optimize both accuracy and interpretability at the same time. So yeah, and they gave us a little this prize for this, and we were so proud of it that we decided that we would submit the paper to a journal, and we were told to email the editor of it was a special issue for a journal, and we were told to email the editor. And so we emailed the editor and we said, "Dear Fancy Esteemed Professor at Fancy Esteemed University, we wrote this paper on this, challenge that we did. We don't know whether our paper fits into the scope of the special issue. It's not a traditional methodology paper. Its contribution is an analysis of this FICO data, including a machine learning model that's interpretable, and it won this nice award." And we thought, hopefully the editor will like this. And the editor wrote back, "Dear Cynthia, thanks for reaching out. This is an interesting paper, but I'm afraid it's not a good fit for the special issue. It's also related to my own recent work on explainability of neural nets. Is the FICO data still available? If so, could you share it?" And I was like, oh man, I sent the guy a paper saying, you don't need a black box for this data set. And he sends me back an email saying, I don't care about your work, but can you send me the data so that I can create a black box for it and explain it. And so I thought, oh, just, people just sometimes don't get it. So anyway, after several years of this nonsense, I finally just got so, that I wrote a paper called Stop Explaining Black Box Machine Learning Models for High Stakes Decisions and Use Interpretable Models Instead. And the earlier version of it was, please stop doing this. But then they made me take out the please. And so it sounds more commanding, like, just do this. And so, in this paper, I gave a bunch of reasons. And there are reasons that I've told you today, which is first that black box models still force you to trust the data set. Also, even if you explain them, you still got to trust the data set. There's also this issue of double trouble that I told you about earlier. You have to rely on two models instead of one, the black box and the explanation. If either one of those models goes wrong, you can't trust whatever's coming out. Those models have to disagree with each other, because if they don't, you could just throw out the black box and just use the explanation, because if they always agree with each other, just use the explanation as an interpretable model. And so often people would write papers, they'd be like, oh, our explanation's right 90% of the time. But hey, that means you can't trust what it's doing 10% of the time. So not good enough. Also, the explanations are not really explanations. They often don't use the same variables. And there was a big scandal involving this COMPAS data set that I was telling you about earlier. The ProPublica news organization had this big article called Machine Bias, and they claimed that COMPAS depended on age, criminal history, and race. But their analysis was wrong. They explained a black box model incorrectly. So COMPAS possibly only depends on race through age and criminal history. And of course, we'll never know that because it's a proprietary model. And then also, if you can produce an interpretable model, why are we continuing to explain black boxes? Do you really want to extend the authority of the black box, or can you replace it with a model that's actually interpretable? Okay, so I just want to say thank you. I have up here a bunch of different papers that I've talked about today. These two papers are this is the ProtoPNet paper. This is its application to digital mammography. This was just recently accepted to Nature Machine Intelligence. And then this is the paper from Nature Machine Intelligence that is like, stop explaining black box models and use interpretable models instead. This is a review paper on interpretable machine learning that is in press in statistics surveys. And then these two papers here are about the 2 helps 2B score. This is the technique that allowed us to design it. And then this paper is the 2 helps 2B score paper. And then this one down here is our most recent paper on decision trees. So this kind of follows up the work on corals we did so long ago and produces optimal sparse decision trees. So thank you very much.
So thank you, Cynthia, for the fantastic talk. And we have a lot of questions, both in the chat and as well as in the Q&A. Would you want me to read them out, or would you like to pick the questions you want to answer from the Q&A panel?
I'll do my best. I'm going to start with the Q&A here. Okay, we're talking about interpretability, and I agree explainable AI has challenge. Okay, my question is how we're moving into accountable and credible AI using interpretability. That's a good question. So there's also the issue of fairness. So there's accountability, fairness, trustworthiness. And I think a lot of these, for me, interpretability opens the door to a lot of these. So in other words, I have a very hard time understanding how a model could possibly be fair if it's not also interpretable. I also don't really understand how a model can be really, I don't really know how you can talk about credibility if the model's not interpretable. So I think these questions are important, and we need to answer them. And this is interpretability. Like I said, I think it's something essential for those questions. Accountability gets into sort of legal issues as well, which, yeah, I depend on lawyers to answer those kind of questions. Okay, is the interpretable deep learning model with an interpretability layer adversarially robust? Yeah, that's a good question. Because if it actually uses prototypes, it should not change classes easily depending on unidentifiable noise. So I was approached by somebody who works on robustness and adversarial learning to talk to me about using Proto-Peanut for it, and one of my students was real excited about that. I don't know, I think it did a project on it. But I think if you want to make something robust, so first of all, you have to do a ton of data augmentation. You have to absolutely make sure that it's robust. That's not something we did for our training because we were just trying to prove that you can get an interpretable model of the same level of accuracy as a black box. So that's what we're trying to prove. We proved our thing. But if you want to actually have it be robust, you have to train it in a way that's robust. Another thing is that if you do have the interpretability, you can prune out prototypes that are bad. So you can make it more robust. For instance, sometimes like with water birds, we'll see water prototypes. They'll be like just a picture of water. And, it's using the information about water to figure out that it's a water bird, but that's not going to be very robust. So we might want to prune that prototype out. Yeah. Okay. Let me keep going here. Let's see. When we talk about the accuracy of a black box system and ask ourselves how accurate is it, the first question is how accurate in what? Because we don't know whether the model is focusing on the requested desired pattern or focusing on some other confounding factor. Yes, you are exactly right. So that's why saliency is not good enough, because saliency will show us where the network is looking, but it doesn't tell us what it's doing with that information. And so by creating these comparisons of parts of images with parts of prototypes, it's telling you what the reasoning process of the network actually is. It's saying, I'm making a comparison of this to that. And so it's telling you exactly what information it's using. For the mammography project, since we don't have very much data, we only have data from Duke Hospital, which is just like, it's like a little over 1,000 patients. For that, we had a lot of problems with having it focus on confounding factors. It was looking at healthy tissue and saying that and making judgments about the lesion, and that is not what we wanted it to do. So it was focusing on confounding factors. And so what we did about that was we had radiologists do some extra labeling on the images and told the network, you need to focus here where the radiologists say you need to focus. And that was able to improve both our accuracy and our interpretability by doing that. So yeah, I agree with your point. Okay, what's the underlying machine learning model for 2 helps 2b? So the model is called RiskSlim. I actually showed you RiskSlim's optimization problem in the slides. And I showed you a slide at the very end of the talk that had the name of the paper. The paper is called Learning Optimized Risk Scores, and we've used it not just for the 2 helps 2b score. We've used it for problems in measuring cognitive decline, like measuring Alzheimer's and dementia. We've used it in ADHD ADHD screening. We've used it for sleep apnea screening, and we've also used it for criminal recidivism. So that method has really been quite useful for us in real applications. Okay, you showed the mathematics in which was shown that lambda j is between -10 and 10 as integers. What will happen if you change that? You can change it. For the 2 helps 2b score, it didn't matter because it only chose values of 1 and 2. So you could change it to -5 and 5, and it would just produce the same result because the optimal solution had 1s and 2s in it. But yeah, you can constrain it any way you like with this method. You just plug in those numbers yourself. It's just parameters in the code. Okay, the approach of prototype-based reasoning requires labeling effort. No, it doesn't. It's actually just plain old supervised classification. We just took a benchmark data set, threw it into this thing, and off it went. It figured out the prototypes by itself. So there's no additional labeling effort to use that technique. Although, like I said, with digital mammography, we found that we weren't getting very accurate results. And so we asked the radiologist to label extra stuff in the image. But the black boxes and the interpretable models were both using that the bad information. So they're not any different. Yeah, so there's no extra need for labeling on that. Okay, can interpretable models be applied to domains where specific priors aren't available? Okay, so that is the question that haunts me at night, that keeps me awake. So I've been working in the last couple of years with material scientists. Now, in material science, we don't actually know what it means to be interpretable. So we're trying to do interpretability in an unsupervised way, which is really hard. And we're also trying to do things like, unsupervised concept discovery. So in our review paper, we outlined a bunch of different challenges for interpretable machine learning, including the idea of what would happen if you just have broad information about what would be interpretable and not have really specific information like sparsity or, case-based reasoning or something like that. And so, yeah, I think this is the frontier of interpretable machine learning, is to answer this question where you don't really know what interpretability means. So thank you for asking that. Okay, since you mentioned COMPAS, I'm curious whether you've tried using interpretable models for recidivism risk. Okay, yes, I can definitely point you to that paper. In fact, I had been working on recidivism before the ProPublica article came out. I was one of the very first people working on interpretable models for recidivism. Okay, interpretable machine learning models for recidivism. There's a lot of other stuff on recidivism. Okay. All right, so I'm just gonna share. Can I share my screen again really quick? Let's see. Okay, I'm just going to my website. This is just my website here. Okay, so this is my website. So I'm just gonna, okay, so I have two recent papers. I have this one, which is on interpretability and fairness. This paper is on the mess with the COMPAS score that I mentioned in the talk. It's called The Age of Secrecy and Unfairness. And the word age is a joke there because it's all about the age variable. Okay, and then this is the paper from 2017. It's called Interpretable Classification Models for Recidivism Prediction. And here what we showed was that you don't need black box models for recidivism prediction. And we also pointed out in this article back in 2017 that age and criminal history were correlated, or criminal history in particular is correlated with race. And so you got to be really careful if you want to try to take race out of these models, because you can't just leave criminal history in and say that it's not correlated with race, because actually, race is actually embedded in these models. Okay. Yeah, so that answers that question.
Cynthia, we have one of our panelists who has a hand raised. Could you take that?
Okay, great.
Thank you.
Hello, you're able to hear me now?
Yeah.
Yes.
Yeah, okay. So, hi, Cynthia. I have a small question here. So, the significance of explainable AI is that it makes programmers responsible for what their models would do, right?
What?
Yeah, the significance of explainable AI is that it makes programmers responsible for what their models would do.
Well, I guess that's part of it, yeah.
All right. I don't know. I'm just making certain statements, and then based on which my question would come, right? So qualifying in terms of bias contributes to this directly. Would you agree with that?
Bias, like racial bias?
Qualifying this explainable AI in terms of bias would contribute to this, right? So bias can have its roots in algorithms, in data sets, and even in businesses, right?
Yeah.
Yeah. So it is also inherent in every human observation.
It's inherently
it's in every human observation. That's an inherent bias in that, right? So it's a natural phenomenon, and we can't fault it. Rather, we have to live with such biases.
Well, we don't necessarily have to live with biases. We can try to correct some of them.
Correct. I mean, in the sense that my question is this: there are various sources and aspects of bias, right? So how should we be dealing with explainable AI instead of qualifying it? Are there any methods to quantify bias and then say, hey, this is your bias factor, this is your bias code, whether you want to live with it or not, or whether you want, is it acceptable or not, it's something else that we could decide later. So something to quantify bias, is that possible?
Yeah, so there's, okay, so in terms of like bias against certain groups of people, there's a whole field of algorithmic fairness that quantifies different kinds of bias and different types of fairness, okay? So fairness is, it's a separate issue from interpretability, but like I said, I don't think that you can have fairness without interpretability. So, you can use all of these metrics for fairness and bias, and I think you should. But without understanding what the models are actually doing, it's hard for me to believe that they can truly be evaluated in terms of fairness.
All right.
Yeah.
Okay. Yeah. Thanks, Cynthia.
Yeah. Thank you.
So Cynthia, we are at time, but there are still a lot more questions. If you, it just depends on whether you would like to spend a couple of more minutes answering the most interesting of the.
Yeah, I'm going to keep answering. If you guys have more questions, I'm going to stay until they're answered.
Oh, great. Fantastic. Thank you very much.
Yeah. Okay, so let's see here. So I answered a bunch of these ones. Okay, doesn't stack. Yeah.
I was just going to point you where you left off. Yeah, you got it. Yeah.
Okay. Doesn't stacking interpretable models make the result less interpretable? Yes, they do. And how do we interpret stack models? So it's still case-based reasoning, but I guess if you think about it, the world for the last however many years, since 2012, has been focused on designing more accurate black box models. Like you have the entire world training these things, whereas how long did we have people training interpretable models? Right, a year with my 2 graduate students for these particular neural networks. So yeah. If you stack these things, it's less interpretable, it's not as sparse. But if we have more people training them, we could potentially make it more sparse and still maintain that accuracy. So I think just the fact that we were able to do case-based reasoning and still get, that same level of accuracy, that's something I'm proud of. But you're right, we can definitely do better in the future. And maybe, maybe people who can do that. Actually, I should say though, there have been a few hundred papers that have extended Proto-PNet in ways that trained it actually better. So there was a group that extended our work. There's a couple of groups whose work extended Proto-PNet that I was jealous of. I was like, oh man, I wish we had done that. So one group put a decision tree at the end instead of a linear model, and they were able to get really great accuracy with really sparse explanations. And then there was another group who extended it to time series, and they were also able to get really good explanations. So like I said, now we've got the world training more interpretable models, and hopefully we're going to be doing better. Okay, and how are the prototypes identified? They're actually identified during training. So I skipped over the technical details of how it works, but I'll tell you a little bit about it since you asked. So what happens is that you map everything into the latent space, right? You use the CNN's filters, many layers of filters to map into the latent space. And then the prototypes are actually points in the latent space. And most of the time, points in the latent space don't correspond to real images. And so what we do is every once in a while, we just take one of those prototypes and snap it back to projection of a real image. And so, you sort of, and then you let it loose, you let it kind of wander around the latent space and then snap it back every once in a while to a real image. And so those real images are the prototypes, and that's how it's trained. So the prototypes are not chosen by a human. They are all trained just like the rest of the network. It's, like I said, it's kind of like k-nearest neighbors. you don't train who your neighbors are. You find them. Okay, let's say for misclassified instances. Oops, where'd it go? Come back. Okay. Let's say that for misclassified instances, misclassifications due to assessing high similarity on a wrong part, right? Yeah, so it messes up, which is, I showed you an example where it messes up. Okay, so say we have some annotation saying some specific parts being left out from being assessed. As highly similar was the reason for misclassification. Can we use this information to correct our interpretable neural network? Yes, you can. Thank you for asking this. Okay, is there any work in this direction? So this is exactly this is exactly what happened in our mammography project. So in that project, like I said, we were using healthy tissue to assess what was like healthy tissue over here to assess what was going on in a breast lesion over here. That was bad. And so what we did was we hired a bunch of radiologists to label some of the training images very, very carefully, and that told the network where it should look. And so we retrained the network afterward and forced it to look at those specific parts of the image and not to look at the healthy tissue. And it still was able to maintain its accuracy with respect to what we had before, and with respect to the black box. So yes, that is exactly the work in this direction. And the paper again is one of the ones I showed you. It's IAIA-BL, which is our interpretable deep learning model for digital mammography. Okay, let's see here. Where were we before? Where are we now? Let's see.
Why changing from DenseNet 161 to VGG 16 work?
Yeah, I don't know. I'm not sure why one deep learning model is more accurate than the next. It's kind of an overall challenge in machine learning to figure out which model is going to work better than which other one. But luckily, you don't really need to make that. You don't really need to ask that question because you can just run them all. They're not that expensive to train, so you can just run all of them and see which ones are more accurate. So it's I don't know the answer, but I'm not sure that it matters that much. Yeah.
Can we have interpretable probabilistic models? I'm just reading the last two questions. Okay.
Yeah. So a bunch of years ago, I was a Bayesian modeler. I switched back to optimization in the last few years, but you can. So for example, the corals method that I showed you at the beginning started out as being Bayesian rule lists and sort of evolved. Bayesian rule list is fully probabilistic, so every part of that method is probabilistic. There's a probability distribution over decision lists, and then the rules themselves, each rule, its predictions are probabilistic. So it's definitely possible. There's a bunch of work that I'm not involved in on interpretable uncertainty quantification for sort of other types of models. I guess decision trees are very easy to, when you're thinking about uncertainty quantification, decision trees are fantastic because if you're in a leaf, then you're predicting a constant, you're predicting something in a leaf, and you can compute probabilities within the leaf. And that makes your life a lot easier. Were you thinking of something very specific type of model or specific type of uncertainty quantification, or did I answer your question?
I think so. I mean, I'm just reading out questions here, and I don't think the person who wrote the question did not specifically give more details. Okay. So there's another question. So what are the things to consider while building an interpretable model for clustering?
Oh boy. Oh, that's a good question. So for clustering, you might want. So I haven't worked on interpretable clustering. So when you go to unsupervised methods, it gets to be kind of challenging what interpretability means. So for clustering, you might want to have specific features that designate the cluster. So you might say, like, for everybody who has been delinquent for more than 3 times on their loans, they fit into this cluster. And for everyone who has this and this characteristic, they would go into this cluster. So you could sort of do it that way, where the clusters are defined by rules on the features. but it depends, like I said, it depends on the type of data, because like for images, that doesn't really work. Not sure. For images, you might say, well, everything in this cluster looks like this prototype, maybe. I don't know. I think that's a really good question. It's definitely worth studying. I haven't done it. I think whoever asked this question, you should totally do it.
Yeah. One final question. Is there any hope for an axiomatic framework for interpretability? And how important is the human to whom the interpretation is done?
Okay. So the second question is more interesting than the first one there. So the second question is, how important is the human? And the answer is, the human is incredibly important. So interpretability is completely subjective. And you have to choose the interpretability metric depending on the domain, on the data, and on the user. And there's no way around that, and it's incredibly important. So that answers the first question as well, which is, can there be an axiomatic framework? There are a lot of papers right now that are really into these like taxonomies and like, this is, you know, if you're doing this, follow this taxonomy. I can't stand those papers. I really don't like that idea, because the problem is that for every taxonomy you could come up with, I can come up with a problem that doesn't fit in that taxonomy. And most of the time when I'm working on a real problem, it's not going to fit. So the way I like to think about it is that interpretability metrics are kind of like performance metrics. Like when you're working on a data science problem, what's going to be, how do you pick your performance metric? You could use accuracy, weighted accuracy, balanced accuracy, RSC, or AUC, weighted area under the ROC curve, partial AUC. You can use precision, you can use recall, right? There's so many different evaluation metrics. How do you pick the one for your domain? And the answer is, I asked a domain expert. Well, guess what? That's what you have to do for interpretability as well. You have to pick your interpretability metric based on the domain and what the domain expert says. So, you know, there's no taxonomy for regular machine learning, right? There's no taxonomy for all of statistics. So I don't see why there needs to be a special taxonomy for interpretability. I think it can just fit into the real world and the real world problems in its own sort of organic way, if that makes sense.
I think, Cynthia, there was an accent issue here. I don't think there was a taxonomy in the question. It was about axiomatic framework for interpretability. It's there in the chat window. The question was in the chat window.
Oh, but see, like the papers that are sort of creating this axiomatic framework, they're also the ones doing the taxonomy. So I actually, there wasn't an accent issue. I understood you perfectly. Okay, no, sorry, I was just going one step further.
Sorry, I kind of misunderstood.
Yeah. I mean, I've been trying to limit my axioms to simply an interpretable model is constrained so that you can understand it. Like it's just one axiom. That's it.
I mean, just a follow up to that, right? From the examples that you spoke about today, I mean, could you give an example of how the interpreter played a role, the human played a role?
So like for the breast cancer one, I've just spoken about that several times where, you know, we looked at the images and we were like, no radiologist in their right mind would use this model because it's looking at the wrong part of the image. So, you know, we're gonna fix it so that it makes sense. I guess I do have 5. So in the paper that I introduced earlier on, in this review paper over here, the fundamental principles paper, it does have 5 principles. The first one is just interpretable models are constrained, you know, and then the other principles are like just try not to explain black box models and, you know, stuff like that. So it's really pretty, you know, it's like not trying to give everybody a pile of rules they have to follow, right? It's more sort of opening up the space so that people can do whatever is necessary for their domain.
Okay. So I'm really thankful that you stayed back for so long and took all the questions, and thank you on behalf of the audience and us for spending so much time and for this wonderful talk.
My pleasure. Thank you for inviting me.